Welcome aboard, aviators. In today's video, we are exploring one of the most powerful tools in a pilot's cockpit, the Airborne Weather Radar. From detecting storms miles ahead to mapping terrain and helping us stay clear of turbulence, the AWR is a system every pilot must understand. So let's dive in and break it down, step by step. This system is one of the most important tools a pilot has on board, because it gives us vital information for weather avoidance and navigation. But here's the thing, the radar only shows us the data. To use it effectively, a pilot must know how to interpret and understand what they're looking at. So what exactly is AWR? It's a primary radar system, which means it works on the echo principle. In simple terms, the radar sends out a signal. That signal bounces off weather phenomena or terrain, and the returning echoes are analyzed. From this, the radar paints a picture of what lies ahead, giving us a chance to avoid dangerous weather and fly safely. Now, let's look at how the Airborne Weather Radar actually works. Most AWR systems operate at high microwave frequencies, usually around 9375 MHz to 10 GHz. These frequencies are chosen because they provide the right balance between range, accuracy, and weather detection. So what can the AWR really do? Let's break down its key functions. First, it can detect and measure water droplets. This tells the pilot not just where clouds are, but also how dense they are, which helps in spotting areas of potential turbulence. Second, it helps in determining cloud top height. By adjusting the tilt of the radar beam, a pilot can actually figure out how tall a storm cell or cloud formation is. Third, the AWR is also useful for terrain mapping. It gives a clear picture of the ground below, which adds an extra layer of safety by helping avoid high terrain. And finally, it can assist in position fixing. By providing range and bearing information relative to prominent geographical features, it can help a pilot confirm their position when needed. So as you can see, the AWR isn't just about weather, it's also a versatile tool that supports navigation and safety. The heart of the Airborne Weather Radar lies in its antenna, which is usually placed in the nose of the aircraft. Now, this antenna can be of two types: a parabolic antenna, which looks like a dish and produces a very highly directional beam, or a flat plate antenna, which is designed to give specific beam patterns depending on the requirement. When it comes to the radar beam itself, we mainly use two types in AWR. First, the pencil beam. This is a narrow and concentrated beam, perfect for weather detection and long-range mapping, especially beyond 60 nautical miles. Here, you could imagine a thin laser-like beam projecting straight out from the nose of the aircraft. Second, the fan-shaped or cosecant squared beam. Unlike the pencil beam, this one spreads out vertically, giving us a wider coverage area at shorter ranges. It's primarily used for short-range mapping and ground mapping. Think of it like a fan of light spreading downward, covering the terrain below. So, depending on whether we want long-range weather detection or close-range ground mapping, the radar switches between these two beam patterns. Most commercial weather radar systems operate at a frequency of about 9375 MHz, with a small tolerance of plus or minus 30 MHz. Now why this frequency? Because it gives the best radar returns from large water droplets and wet hail, the exact things you'll find inside powerful convective clouds. And here's why that matters. Large water droplets and wet hail are closely linked to severe turbulence. In fact, these droplets can be as large as 3 centimeters or more in diameter. So when the radar picks them up, it's a big red flag for pilots. Modern airborne weather radar also uses color coding to show rainfall intensity. This makes it much easier for pilots to quickly interpret the severity of weather ahead. Here's how it works. Black means very light or no returns, essentially safe skies. Green shows light rainfall, between 0.4 and 4 millimeters. Yellow indicates moderate rainfall, 4 to 12 millimeters. Red is a warning sign, strong rainfall, over 12 millimeters. And magenta is the most dangerous, it indicates turbulence caused by extreme rainfall intensity. So with just a glance at the colors on the radar screen, a pilot can immediately judge where the safest path lies and where the severe hazards are. When it comes to thunderstorms, the Airborne Weather Radar backquote can reveal hidden dangers by showing us the shape of echoes on the screen. One of the most important clues to turbulence is the rainfall gradient. If you see colors changing rapidly, for example, green to red to magenta in a very short distance, that's a strong sign of severe turbulence. But beyond just colors, pilots must watch out for specific echo shapes that are strongly linked to hail activity and dangerous convection. The first is the V shape. If the radar echo forms a clear V, it's a classic sign of intense convection and potential hail. Next are fingers. These are elongated, finger-like projections extending from the main echo. They usually mean there are powerful updrafts and downdrafts, pointing to severe turbulence. Then we have scalloped edges. When the outline of the radar echo looks wavy or irregular, it often indicates intense wind shear inside the cloud. And finally, the most dangerous of all, the hook echo. This hook or comma-shaped radar return is a classic warning of a rotating storm, often linked with tornadoes and violent thunderstorms. The golden rule for pilots? Avoid these echo shapes at all costs. They are some of the clearest radar warnings of hail activity and extreme weather. Now let's take a closer look at the controls of the Airborne Weather Radar system. These allow the pilot to optimize how the radar works and how the display looks. First, the power switch. When it's set to on, the system comes alive and the antenna is automatically stabilized in both pitch and roll. This means that no matter how the aircraft moves, the radar beam stays steady. But if we select stab off, the antenna is locked directly to the aircraft's pitch and roll. Pilots usually use this during climbs or descents, when the aircraft's attitude is changing quickly, so the antenna isn't constantly trying to correct itself. Second, the range switch. This lets the pilot choose the radar's range setting, and it energizes the transmitter accordingly. There's one very important rule here. When the aircraft is on the ground, the radar must be kept in standby. Otherwise, strong echoes from hangars, equipment, or even ground personnel could damage the system. The radiation is powerful enough to heat or even melt circuits. Third, the tilt control. This allows the pilot to tilt the radar beam up or down, usually between plus 15 degrees and minus 15 degrees. By adjusting this, the pilot can scan vertically, for example to check the tops and bases of cloud formations. And finally, the manual gain knob. This control adjusts how sensitive the radar is to incoming signals. Higher gain means weaker echoes, like light precipitation, become visible. But remember, when features like swept gain, sensitive time control, or automatic gain control are active, the manual knob is overridden. These automatic systems adjust sensitivity on their own to prevent the display from being overwhelmed by strong, close-range returns. In short, these controls give the pilot the flexibility to tune the radar depending on the phase of flight and the type of weather they are dealing with. The Airborne Weather Radar comes with different operating modes, each designed for a specific purpose. Let's break them down. First, Map Mode Ground Mapping. This mode is used mainly for navigation and surface mapping. It relies on a fan-shaped cosecant beam, which spreads out vertically to cover the ground below. Here's an interesting detail. As objects get closer, the transmitted power is automatically reduced. This prevents strong nearby reflections from overwhelming or damaging the antenna. Map mode is most effective between 50 to 60 nautical miles, though the beam itself can cover from about 15 up to 70 nautical miles. On the display, it paints surface features and helps with terrain awareness. Second, Weather Mode, also called Long Range Mapping. This mode switches to the conical pencil beam, which is narrow and precise. It's perfect for detecting and mapping cloud formations, usually between 70 and 150 nautical miles ahead. Pilots use this mode to spot weather cells early and plan their route around them. And third, Contour Mode. This one is all about emphasizing areas of heavy rainfall and turbulence. The display changes to black and white, with darker shaded areas, often called black holes, showing zones of concentrated rainfall and dangerous turbulence. It's an iso-echo display, meaning it highlights areas of equal radar return intensity, so pilots can immediately identify the most hazardous weather inside a storm system. Each of these modes, map, weather, and contour, gives the pilot a different perspective, ensuring the radar is not just a weather tool, but also a navigation and safety system. When it comes to using the Airborne Weather Radar, there are a few practical considerations every pilot needs to keep in mind. The maximum practical range for weather detection and navigation is usually about 150 nautical miles. Some modern systems can even push this up to 300 nautical miles. But in reality, most weather avoidance decisions are made well within that 150-mile range. Now let's talk about the most important part, avoiding thunderstorms. Radar doesn't just help you see the storms, it helps you keep a safe distance from them. And that distance depends on your altitude. If you're below 20,000 feet, stay at least 5 nautical miles clear. Between 20,000 and 25,000 feet, increase that to 10 nautical miles. From 25,000 to 30,000 feet, the minimum clearance should be 15 nautical miles. And once you are above 30,000 feet, give storms a wide berth, at least 20 nautical miles. And don't forget vertical separation. Always keep at least 5,000 feet above or below the top or bottom of a thunderstorm. The key takeaway? Never cut it close with weather. Even if the radar makes the storm look manageable, the turbulence, hail, and lightning inside can be far worse than what the screen shows. And that wraps up our discussion on the Airborne Weather Radar. From storm detection to terrain mapping and safe avoidance techniques, we've seen how this system plays a crucial role in every pilot's journey. At the end of the day, the radar gives us the picture, but it's the pilot's skill and judgment that ensures safety. For more aviation knowledge and guidance, follow Aerominds Training Center, your destination for aviation learning and updates. Fly safe and keep learning.